Principal components is a data reduction technique. So again, we're going to have a set of variables and we want to reduce them into what we're going to call components. But in factor analysis, we would call them factors, which represents the variable's variance. So most of the time people will do a principal components to reduce the number of data that they have into those components, and then they use those components as part of an analysis or is a check before you run another type of analysis. So I do a lot of what's called Roche analysis. So one of the assumptions of Roche analysis is checking for unidimensionality, just one dimension, and the construct and the way that you check would be using principal components. What are the differences between EFA and PCA? So they look the same, but they're not the same. So one important difference is that there's no rotation in PCA. So that's always nice because there's always that complexity of which rotation am I going to use. So here you don't have to be bothered by the rotations. PCA, you tend to use it for non-latent variables, and EFA is used for latent variables. So PCA is for variables that we can measure, and EFA is for variables that they're going to be self-reported, basically. When we do EFA, it has a lot of steps. So there's a planning phase where we want to see if our data is suitable for EFA. And we check those assumptions like Bartlett's test and KMO, that's the other one. So see if the correlation matrix is adequate for running EFA. And then their second step is actually getting the factors, extracting the factors. The third one is deciding how many of those factors we're going to keep and then naming them. The fourth one, somewhere in the middle, we rotate them. And for PCA, it's just the second step. We're just going to extract the factors and that's going to be it. So the number of variables that we retain are going to have the maximum, as much of variance as possible from the original variables. So that's enough for us to do whatever we want to do with it. It could be just running the PCA, or it could be using the PCA as part of an analysis. So we can use the PCAs as an assumption check for a different analysis, or we can use PCAs as we can do an analysis on them. So here I have a decision tree on how to select PCA or EFA, and essentially it's just asking, do you need data reduction? If you do, you can do PCA or EFA, and then what type of data do you have, latent or non-latent, and that's going to decide between PCA and EFA. You can also do both and compare how they work with the data that you are using. The assumptions for PCA are pretty similar to EFA. We have to check sphericity using Bartlett's test, and we have to check the sample adequacy. Is the sample adequate for running EFA? And that's what the Kaiser Major Olin, I think it's, criterion is going to tell us. And then we have to check that the determinants are going to be positive, because we are doing a lot of matrix algebra behind the scenes. So we just want to make sure that whatever transformation that we do to our matrices, that the determinant is going to be greater than 0, and it's not going to give us an error. The kinds of research questions that you can answer using PCA, here I have a couple of examples. What survey questions should be grouped together that best measure X, Y, and Z domains? So here we have 3 dimensions. Should sections of X and Y account for any variance in the C domain? How many components? You just want to see how many components there are in the data. This is very exploratory, and most likely the first example is about intelligence test. So we have a data set with 161 sophomores who were given 5 intelligence tests. This measures our inductive reasoning ability for letters and numbers, figure relations ability, as well as Raven Advanced Matrices test. I have no idea what that is. That's so Raven. And a cultural free test. Okay. And the research question is, how many components can we extract from this data set? The data is available in the PCA.dat file, so it's a text file, and you have to use the from text base option. So this is what the data would look like. I have some code here where I give names to the columns, and then I just save everything as a matrix because the functions that we use for PCA, they require a matrix, so that's why I have to transform it into a matrix, and I do that by doing as dot matrix. And here I just show you pieces of the data. This is the first 10 observations. This is the last 10 observations. So what I like about this data is that it looks pretty continuous. So always data screen first. We're going to check if we have missing data. And it says false, so we don't have any missing data. Remember, one of the assumptions that we have to check is the determinants are greater than 0. So here I'm going to store the correlation matrix. I'm going to ask for the determinant, and it's greater than 0. Barely, but it is greater than 0. Same for the covariance, greater than 0. So we're cool. That's a good thing. We meet that assumption. Don't write we're cool in your paper. I'm also going to check the correlation matrix, and I'm going to use the PSYC package just because I want to see if the correlations are significant. I personally am not a big fan of attaching significance to correlation. I think it's very easy to do when you have enough data. But it is something that we report, and for principal components, I've seen a lot, like people report the significance of the correlation between the variables. We want them not to be too high, like 0.90. We don't want them to be too low, 0.1. We want something nice in the middle that doesn't give us any problems. So I use the package HMISC and the function rcore, and then I put as.matrix PCA. It gave me the correlations between the variables, and this is just the p-value is very small, so they're all significant. Very nice. I didn't see, yeah, they're not too high, they're not too low, they're really, really nicely correlated. Can't believe I just said that. The power analysis and sample size for PCA does not exist. GPower definitely doesn't have the option to do a power analysis for PCA. You can use the rules of thumb that I'm going to show you right now. So there's a 20-to-1 rule of thumb. For example, 5 variables times 20 subjects, I would tell you, that would give you 100 observations total. There's another author, this is an SPSS textbook a lot. Survival SPSS something. Ideally, you would have 150 cases total, at least 5 cases for each variable. As always, larger samples are better and recommended, and then having 10 to 20 observations per variable should be enough. So you can cite any of those when you are conducting your own PCA. Assumptions. So the sampling adequacy KMO criterion, it stands for Kaiser Major Olkin. I said Olin before, but it's Olkin. A measure of sampling adequacy. It indicates the proportion of variables in your variables that might be caused by underlying factors. So we're looking for high values here. Generally, a high KMO would indicate that you can use factor analysis, or in this case, principal components with your data. A low value of 50 it's probably not the best course of action to do a PCA or an EFA. And there's newer research that suggests that 0.7 might be enough. So if you're borderline 0.7, I would do a little search in Google Scholar. There's a fairly newer research that indicates that 0.7 should be enough. So we're going to use the library umbrella for that to find our KMO. We're going to use the function path PAF. We put our PCA data here. We just leave those options here for the eigenvalue criterion and the covariance criterion. This function, I'm going to store everything into paf.pca. And I'm only going to ask for dollars on camo because there's so much information stored in there. I just want to see the camo. And it's closer to 1. It's greater than 0.5. I'm happy. That means that I meet the assumption and my data is adequate for PCA. The next assumption is the correlation adequacy. It's also, you can also think of it as sphericity. So we're going to use Bartlett's test of sphericity to test the hypothesis that the variables are unrelated. That's the null, and the alternative is that the variables are related. In the multivariate verse, what we're doing is that we're comparing our correlation matrix to the identity matrix, and we're going to see if there's a difference. If we reject this test, then that tells us that we can go ahead and use EFA or PCA with this data. And I really like this test because the output is super clean, which is not common with R. So it's core-test.bartlett, and then we put our correlation matrix inside, and then we have to tell it the sample size for some reason. I don't know why I can't just do it, count it by itself, but okay. Here I see that I have a very small p-value. So I reject the null hypothesis. The variables are related. And remember, we're trying to find the relationship between the variables by doing PCA. So that's what we want. This tells us that the data is adequate for PCA or EFA. So for our data analysis, we're going to use the PSYC package and the principal function. So here I have principal. I'm going to store everything into PCL model 1 because I'm looking for one component. I am giving it the correlation matrix and I'm asking it not to rotate. And then I just call for that variable. I highlighted the pattern matrix just in case you have to do PCA in a different software. That's the matrix you would be looking for. So here's the first component. And these are going to be the weights that we use for when we create the principal components equation. It also has an H2 column and a U2 column, not the band. And then here in proportion of variance, it tells us how much one component explains. So one component explains 76% of the variance. Now let me explain the two columns next to the principal component. So one was H2 and the other one was U2. So H2 is how much the common or shared variance between the variables explains of the factor structure or contributes to the factor structure. And U2 is how much that individual variable contributes to the factor structure. So ideally, you're going to have H2 be greater than U2. If it's not, it's probably a problem. It would mean that there's no overlap here and the variables are very separated. And then you begin to question why you're doing principal components, because the whole point is to see how much these 5 variables explain of that whole factor structure. So the H2 are called commonality, the shared variance, and the U2, the unique ones, are called the residual variance. It's really what's left once we account for the overlap in the variables. So I went ahead and did another principal components, and I did it because your textbook suggested it. I think it was just to show you that you can control the number of components that you ask for by using this option, and factors equals 5. So here I would be looking for 5 factors. And you can see PC1 to PC5 and then the H2 and U2 columns. But you can see that for the first component, nothing changed dramatically. Here I have again the 5 components, and more importantly, when I look at proportion of variance, let me highlight that. There's 2 proportions of variance. If you were doing EFA, you would look at this one. We're doing PCA, so you're looking at this one. So one component explains 76% of the variance. And then if I add a second component, it doesn't help. It gets worse, worse, worse. So even though we forced it, the one component solution was the best one. The only reason we got all this output was just because we asked for it, but it didn't seem to help the model. So our next step is going to be to get the scree plot. So scree plot is a plot that helps us find the number of desirable either factors of components for EFA or PCA. The y-axis has the eigenvalues, the x-axis has the number of factors, and it usually looks like an L. Ideally, you're looking for the elbow, which would be here, and then you look at how many components or factors are above that. For us, we just have one component, and that's what it looked like from the output of the principal function. I personally find scree plots very confusing. I think they're more art than science, so I always prefer to look at the output, but you can provide it. It's just a good practice to have the commonalities, the scree plot, and then the parallel analysis, which is the next thing we're going to use. So parallel analysis can be used for both EFA and PCA. It's based on a Monte Carlo simulation or just simulation. It kind of generates many data sets similar to the one that we are giving it. And it averaged out the number of components, and then it suggests you should use this many number of components. It's not something that you necessarily have to do in R. I know that Jamovi does it, and there are websites you can just Google parallel analysis, so you can always look for that. In R, the function is going to be FA parallel. I am not giving it the correlation matrix, I'm giving it the raw data. The number of observations, here is just parallel analysis, principal components. If it was EFA, we would change this to FA. And then it gives you the actual data and then the simulated data. For the actual data, it's suggesting one component. And you can see the simulated data doesn't have the deep bend of the elbow, but it does come with an output that tells you the number of suggested components is 1. I freaked out when I saw the NA here, and then I realized, well, I'm looking for components, not factors. Don't be like me. If we were doing EFA, then this one would have the number, and then this one would say NA. So the next thing we can do is create the plot for the principal components. So I use the function fa.diagram, and it gives me this really nice components plot. So I purposely gave it the PC model 2, which is the one that has the 5 components, but remember, we already decided that one component was the best one. I just wanted you to see what it would look like. If we change this to PC model 1, it was going to eliminate this 4 boxes and just point all the arrows to PC1. But you can see even the diagram knows you're supposed to be using one component. The next thing we would do would be create the principal component equations. Remember, we get this one from the loadings in the very first principal function, and then we just multiply it by its variable, and that's how you create the equation. Why would I use this equation? So you can use it to cross-validate, which we haven't really done in this class, but more importantly, remember, principal components, you can actually save them and use them for other analysis, and those analysis can be assumptions for other techniques. So that's what I'm going to show you how to do here. So here I have my raw data, and I'm going to save it as a data frame in PCA2. I just attach it so I can just call it. So here I have the equation that I created based on the component loadings, and it's actually multiplying it by the column Raven, by the column called whatever that was, and so on, and it's storing everything into PC scores. And then I just asked it to sort them, and decreasing false, so it's going to be increasing. And then I call for it, and it gives me the actual scores. And we can do other things with them. We can just save them. We can use them for future analysis. So when I look at PC scores, I have the lowest value, and then I have the largest value. What we're going to do next is we're going to standardize the scores and we're going to use Thurstone C-scores. I think he was a measurement guy. I hope maybe you learn about him in the measurement class. I can only tell you that he's a measurement guy. What we're going to do is that we're going to put our data in a range from 0 to 100. I think this is easier for when you have to present your results outside your bubble. Like, you know what they mean. And maybe people in your department that do similar research know what they mean. But if you have to present it to people outside that bubble, stakeholders, your boss, someone like that, it's just easier to have it in a range from 0 to 100. It makes it more accessible for people that are not doing the type of research that you're doing. So this formulas come from the Schumacher text. You have the wanted range and then the current range. So I want it to be 100, the highest value. And then this is the actual highest PC score from our data. And then it's going to be minus minus the lowest value. And that's going to give us this 0.25 here. Then I'm going to calculate M. So M is going to have the lowest, the wanted low person score, which is 0. And then we're going to put the lowest PC score, which was 66. And we're going to multiply it by what we calculated in S, which is the 0.25, the blue number. And that gives us the 16. So here I just went ahead and did it again in R. This was just to show you where each number was in. Here I actually calculated. Now I'm going to do another PC scale where I put what I calculated in M, which is the 16, plus what I calculated in S, which is a 0.25, times every single value stored into PC scores, and that's going to standardize everything. And then I just rounded everything into 2 digits, so it wasn't a complete mess. And you can see now it goes from 33 to 100, so the maximum score is 100. And I know it's hard right now because the data set that we have, we're not that familiar with it, but once it's your own data, I think you're gonna connect more with it. So the next thing I did was just to create histograms of both PC scores and the standardized PC scores. So this par MF row is just telling R to put the 2 graphs next to each other, so 2 in the same row. And then just histogram for PC score and histogram for PC scale. And you can see the shapes are not that different. You can see this one actually looks a little bit more normal than the raw scores. But really what changed is just the x-axis. We just changed that to go from 0 to 100 instead of 50 to 350, which we wouldn't be able to say what's a good score. Okay, I got a score of 70. Well, what does that mean? But over here, if I look at the score of 70, yeah, like it looks like it's above the mean, which would be over here. So now the write-up, we just say what procedure we were doing, which is principal components. Probably want to say what software we did it in. We had 5 variables. We went ahead and calculated correlations, and they were statistically significant. We checked the assumption of sphericity using Bartlett's test and indicated that their variables were sufficiently related for a PCA. The same thing for KMO. It was close to 1, so that also tells us that the sample was adequate for PCA. Finally, we also checked the determinants. They were all greater than 0. That means that they were positive definite, and that's also good. It means that we can actually go ahead and calculate the PCA. So the PCA indicated a 1 component structure, and that explains 76% of the variance. We also check this by using a scrape plot and a parallel analysis, and they all suggested 1 component for our data. Then I just went ahead and created a little table where I had my variables, the component weights, and then the commonality and the residual variance. I also reported the reliability for the variance, the variables, and I'll show you how to do reliability later. One thing that I wanted to say is that this is a really bad practice to use the software names, variable names for your tables, and I know that I just did it. It's always better if you actually tell the reader what they mean. So don't be like me. The next example is everyone's favorite topic. It's student evaluations. It's a very large file with 67 variables and 1,428 cases. It's actually stored in a SAS database file, so it's going to look weird when you download it on your computer. The data is actually scored from 1 to 5 in a Likert scale. Strongly agree, 1. 5, strongly disagree. When I import it, I call it M255. So to import in SAS, you just go to File, Import Dataset, SAS. So I just checked the dimension, and they are what I said they were. I am only going to get a couple of items, 12 items actually, from the whole data set, and I'm going to store everything into M13. Here I have a couple of sample items. Instructor was well prepared, was confident, was sensitive to students, etc., etc. Then I went ahead and used the summary function to explore my data, and I can see I have a lot of NAs. So I need to remove that. I'm going to check for missing data. I do have NAs. I knew that from just the summary function. I'm going to use the NA omit to remove them. I store everything into M13 no miss. And this is what I'm left with again. Then I'm going to check for outliers. And it turns out I have 58 outliers. And I need to take them out. And I'm going to store everything into M13 no out. And now I'm down to 1,307 cases. Here's what the data looks like, the head and the tail. The next thing I'm going to check is the assumption. I'm going to check that the determinants are positive, and they are. They're small, but they're positive. So that means I'm going to be able to do the PCA. Then I'm going to check for the significance of the correlations. I use the HMISC library. R core, I need to give the data as a matrix, so that's why I put as dot matrix and then my data. And it just gave me a bunch of zeros, and it just means that the p-values are significant. They're very small. So all of the correlations are significant. The next thing I'm going to check is the CAMEL criterion. Again, it ranges from 0 to 1. Closer to 1, that means that the sample is adequate for analysis. I'm going to use the path function. And then I'm just going to call $KMO so I don't have to look at all of the ugly output. Library rel, I use the path function as matrix, and I put my data here after I remove the outliers. And then it's just a summary where I store the output of that function, $KMO, and it's actually larger than what we got in the previous analysis. So closer to 1, that tells us that the sample is adequate for EFA or PCA. Now we're going to check for correlation adequacy, and the way we do that is with Bartlett test of sphericity. Remember, the null is that the variables are unrelated, and the alternative is that they are related. MCR is our correlation matrix. Here it gives me the p-value is significant, so I'm going to reject the null. The variables are related, and we want them to be related in this case, otherwise PCA would not be an appropriate analysis. Then I move on into my actual data analysis. I'm going to show you how to get the eigenvalue. So I've read conflicting reports that reporting eigenvalues it's kind of old school, and we don't do that anymore, but I'm going to show you how to get them just in case you ever need them. So in R is very easy. You just give it the eigenvalue, eigenfunction. You put the covariance matrix in there. Again, there's a lot of output in there, so I'm just going to $sign values. And I rounded everything to 3 just because I wanted to look at it nicely. And you're going to we have 12 items, so you're going to have 12 eigenvalues. The first one is going to account for most of the variance, and then it just keeps on decreasing. And you can just report them in a table. Like, why not? Then I go ahead and do the actual PCA. So I did principal, and I asked for 2 factors. just to see if most of the variance was within the first component and how much. I wanted to see like less point zeros and everything for PC2, basically. That's what I want to see. I told it not to rotate. So this is the first component, and you can see this would be the weights for our equation, principal components equation. So here I can see that one component explains 51% of the variance, and then having two would explain 11% of the variance. So definitely one component is the correct solution here. So let's focus on this output. It's giving you the SS loading. So that 6.17 is actually the eigenvalue for that one component. And then the proportion of variance, we knew it was 0.51, and that's how much variance is explained. So you can actually just call for that eigenvalue by doing PC model. It's stored in BA accounted, and then just bracket 1, and that's just going to give you the eigenvalue. And you can actually find the proportion of variance explained by doing PC model $, where the eigenvalue is stored, divided by the number of variables that you have. So, and that's going to be the 50. So the next thing that we do is just look at the scree plot. I put PC model $ values there, so it's actually the eigenvalues. If I were to interpret the scree plot by looking at the eigenvalues, I can see that there's two factors, which are the little circles above eigenvalue 1. So that could tell me that it's suggesting 2. Or I could just look at really the elbow, which is there's only one factor above the elbow. So that's one way of interpreting it. Let's see what the parallel analysis tells us. So the parallel analysis is actually suggesting 2. It's okay. Like they're not always going to match. You can report the discrepancies. You can say parallel analysis suggested 2, scree plot suggested 1, data suggested 1, the pattern matrix suggested 1, I'm sorry. And then at the end of the day, it's going to be a qualitative decision. Like, what does the theory tell you? Should you have 2 or should you have 1? Then I went ahead and did my plot, and all of my variables are pointing to PC1, and these are just the weights from the principal function. Finally, I'm going to calculate internal consistency reliability. I'm going to show you 2 ways. There's the generic popular Cronbach's alpha, and then there's McDonald's omega for report, and there's like 5 of them actually. I just noticed Cronbach's is the most popular one, and McDonald's omega is the one that's the trendier one nowadays. So Cronbach's is widely used. It ranges from 0 to 1. Closer to 1, it indicates better internal consistency reliability. It tends to underestimate the reliability. Another thing you should always remember is that reliability is not for the scale. You say the internal consistency reliability of the scores for this one particular scale. It's not something that comes with the test. It's sample specific, so just make sure you make it clear in your language. So the same research just says that Cronbach's alpha is underestimating the reliability, and it's slightly biased reliability. Also says that McDonald's kind of corrects for those deficiencies. So McDonald's omega is also from 0 to 1. Closer to 1 is going to be greater reliability. I know there's some macro, so it's kind of like a code for SPSS to calculate it. I know Jamovi has it, and there's this really, really expensive software for structural equation modeling that will give you McDonald's omega. So out of all of those options, it's going to be either Jamovi or R, the free option, of course. So McDonald's omega kind of creates a structural equation model, and that's how it calculates the reliability. That's why it needs structural equation modeling software or a specific code to calculate it. So we can get it from the PSYC package, and there's a function called omega, and it has so much output. Like I was saying, it's actually creating a structural equation model. It comes with a plot and things like that. So I just suppress all that output. So here I just store everything into reliability estimates. I call the omega function. I gave it our data set, the sample size after we remove outliers, and I said plot false because I really didn't want to see the plot. Then I did $alpha to get Cronbach's alpha, and then $omega dot tot. So there's couple of other omegas you can get from this output. Like if you have hierarchical modeling, hierarchical type of data, you can get a different estimate for omega and so on. So there's several omegas within the omega. Just make sure you're looking at omega dot tot. And you can see like it went up for like 0.02. My guess, and I don't have anything to back it with, is if you have a high Cronbach's alpha, you're going to have an even higher omega because it's going to even estimate it more clearly, more accurate. I don't know if that would also be true when you had a lower or medium reliability. I would let you do the research on that. And then here I just have my principal components equation and my write-up. I did a principal components. I talk about the assumptions. I talk about how the parallel analysis suggested two components and discrete plots just one, depending how you look at it. But the pattern matrix suggested just one.